Hi, my name is Bisal Dahal and my university ID is 24812916. This video demonstration is for my module CSY 3062 Cybersecurity and Applied Cryptography. My project is titled Cryptographic Security for a Graduate Recruitment Portal, a practical security report with recommendations for delivering data security. In this demonstration, I will show you 5 live experiments that I carried out in Kali Linux as part of this report. These are GPG digital signature, where I sign a job offer document and then show what happens when someone tampers with it. AES 256 encryption of a candidate CV using Python. A vulnerability scan of a web application using OWASP Zap. A comparison of password hashing using bcrypt versus SHA-256, and lastly RSA 2048 key pair generation using OpenSSL. All of these experiments relate directly to protecting the data of Grado, a recruitment agency in Northampton. Let me begin. Here you can see the 5 experimental folders, four: GPG demo, AES demo, hash demo, and RSA demo. Everything I demonstrate today lives inside this main folder. Now let me show you the candidate CV file I created as a test data. This represents the kind of personal data that Grado would store for our job application. As you can see, the file contains candidate name, their ID, email, and expected salary. This is exactly the kind of sensitive personally identifiable information that needs to be protected. Without encryption, anyone who gains access to the database can read all of this directly. Now let me show you how we can fix that. My first experiment is about digital signatures. The thread I am addressing here is document tampering. Grado sends job offered letter to candidates by email. Without a digital signature, an attacker intercepting that email could silently change the salary or terms of the offer. Neither Grado nor candidate would know. GPG, which stands for GNU Privacy Guard, solves this by mathematically binding this document to the sender's identity. Any changes in the document, even a single character, will cause a signature verification to fail. I already have a GPG key pair generated. Let me show you. As you can see, it belongs to Bisal Dahal with my email address bisalxdahal@gmail.com. The algorithm is EDDSA, which is an elliptical curve digital signature algorithm. This key pair has a public key and a private key. I use my private key to sign documents, and anyone can use the public key to verify them. Now, let me show you the job offer I created for this demonstration. The letter offers Bisal Dahal the role of software engineer at Grado Limited with a salary of rupees 280,000 per annum. Now I am going to sign it. It's asking me the password that I created earlier. Now I would like to show you this one. You can see the document now starts with the header begin PGP signed message and ends with begin PGP signature block. End PGP signature block. That long block of character at the bottom is a cryptographic signature. It is a mathematical fingerprint of this exact document created using my private key. If even one character in this message changes, even if like one of the word changes, then the fingerprint will no longer match. So now let's verify it. The output says good signature from Bisal Dahal. This means the document is authentic and has not been modified since I signed it. Now let me simulate what happens when an attacker intercepts this document and changes the salary. Now I'm going to use the set command to change the salary from 280,000 to 100,000, simulating an attacker reducing the offer before the candidate receives it. As you can see, the salary is 280,000. It's showing now. Now let me set it with 100,000. Now as you can see, the salary is 100,000 as I tampered it. Now let's verify it again. As you can see, the output now says bad signature. A warning message has been tampered. A GPG detection that changed immediately. The signature no longer matches the document because the content was altered after signing. This is exactly what Grado needs. If they sign all the job offer before sending, any tampering will be detected by the recipient when they verify the signature. This is cryptographic document integrity in practice. Now let's clear this. The second experiment is the AES 256 encryption. The threat I am addressing here is the exposure of candidate data if Grado's database is compromised. If personal records are stored in plain text, or database breach means every candidate national insurance number, date of birth, or home address is immediately readable by the attacker. AES 256 fixes this by encrypting the data, so it is completely unreadable without the correct key. AES stands for Advanced Encryption Standard. The 256 refers to the key length, 256 bits. It is the algorithm recommended by the NIST, the US National Institute of Standard and Technology, for encrypting their sensitive data at rest. There are no known particle attacks against a correctly implemented AES 256 cipher. Now let me run the Python script that I created. The script does three things. The first is generates AES 256 key using Python's FAIRNet class, which implements AES 256 CBC with HMAC SAT256 for authenticated encryption. Second, it reads the candidate CV file and encrypts it. Third, it decrypts the ciphered text and confirms the result matches the original. As you can see the output, at the top we can see the generated encrypted key that 64 string. Below that there is the original plain text. You can read the candidate's name, ID, email, and salary expected, and below that there is a ciphered text, the encrypted version. Compare those two. The plain text is completely readable, whereas this encrypted is unreadable. The ciphertext is completely unreadable. Now no words, no patterns, nothing is recognized here. And at the bottom you can see match true. The decryption recovered the original data exactly. This means the encryption and decryption cycle is working correctly. Now let me also show you the OpenSSL version, which produces the binary encrypted file. This is closer to what a real database encryption system would produce. The xxd command shows the binary file as hexadecimal. You can see rows of number and garbled characters. There is absolute nothing in that output that tells you this was originally a candidate CV with the name ID. This is what AES 256 encryption looks like in practice. Now, my third experiment is a vulnerability assessment. Before recommending cryptographic solution, I need to identify what the actual security weaknesses are in the web applications like Grados portal. I used OWASP ZAP, the Z Attack Proxy, which is a free security scanner produced by the Open Web Application Security Project. The target I scanned was DVWA, damn vulnerable web application running locally on my machine. DVWA is a deliberately insecure web application designed for security testing practice. It represents the kind of web application that Grados recruitment portal would be built on. I ran both an automatic scan and an active scan. I would like to open the recent scan. Sorry. The scanner found 13 different security alerts. Let me walk you through the three most significant one. Firstly is the content security policy. The first one that I showed has the level of risk is medium. This means is that the web server is not telling the browser which sorts of script and resources are trusted. Without this header, if an attacker injects malicious JavaScript into a page, a cross-site scripting attack, the browsing has no way to block it. This maps to OWASP A05 2021 security misconfiguration. Now let's look at other one. The second is cookie, no HTTP only flag. This is also medium risk. This means the session cookie, the only that keeps you logged in, are accessible to JavaScript code running in the browser. If there is an XSS vulnerability anywhere on the site, the attacker can steal the session cookie and log in as a victim without needing their password. This is called session hijacking. Now, let's go to other one. The third is server leaks version information. You can see that the evidence field here, Apache 2.4.25. The server is advertising its exact version in every HTTP response. This lets an attacker look up known security vulnerabilities specific to that version and target them directly. This is a simple misconfiguration that takes one line of configuration to fix. These 13 vulnerabilities confirm that without proper security configuration and encryption, a recruitment portal like Grados exposes candidate data to multiple attack vectors. The cryptographic solution I have demonstrated directly addresses the most serious of these, particularly the data exposure and session security issue. So now let's go back. My fourth experiment is about password hashing. When a user creates a password on Grados portal, that password should never be stored in a plain text. Instead, it is passed through one-way mathematical function that cannot be reversed. When the user logs in, their submitted password is hashed again and the result is compared to the stored hash. Now let me run the Python file. There we can see the SAT256 and bcrypt. There is a difference in timing. The SAT256 time is around 0.0107 ms and bcrypt time is 224.49 ms. This sounds like the bcrypt is just slower, but that slowness is an entire security argument. More than graphic processing units, GPU can compute billions of SHA-256 hashes per second if an attacker steals Grazzo password database and all the passwords are hashed with SHA-256. They can try billions of guesses every second. Common password will be cracked within minutes or even seconds. Bcrypt at work factor 12 is limited to approximately 1000 hashes per second. The same attacker now needs year to crack a properly chosen password instead of minutes. This slowness is not a bug, it's the feature. We can also see in the Bcrypt output that the string is stored with $2B $12 that contains the work factor and random salt that was automatically generated and embedded in the hash. Every Bcrypt has a different salt, which means pre-computed rainbow table attackers do not work at all. And at the bottom you can see correct password returns. The wrong password returns false. The verification function works correctly. Now the fifth experiment is RSA-248 2048 key pair generation using OpenSSL. Here is how it works in practice. AES is a fast and great for encrypting large amount of data, but both parties need to share the same key, which is the security problem. RSA solves this by using the public key to secure send the AES key to the other party. Only the holder of the private key can decrypt it. This is exactly how HTTPS and TLS work every time you visit a secure website. The OpenSSL generated a 2048-bit RSA public key and extracted the public key in PEM format. You can see that it starts with begin public key and end public key, and there are like the private key stays on the server and is never shared. Now, the summary that I have demonstrated today, I would like to repeat. GPG digital signature, I signed a job offer letter, verified the signature, tampered with the salary, and so that the GPG immediately directs and tampering with a bad signature warning. This protects Grazzo's contractual document from undetected modification. Second, AES 256 encryption. I encrypted a candidate CV containing a national insurance, a UAN number and personal details. Thirdly, OWASP ZAP vulnerability scan, and the fourth one is Bcrypt versus SHA-256 password hashing, and fifth one is RSA-2048 key pair generation using OpenSSL. And now all of the tools are free and open source and deployed in production system worldwide. The security recommendation in my report are practical and immediately implemented by Grazzo. Thank you for watching. My name is Bisal Dahal and my student ID is 248129116, and this has been my demonstration for CSY 3062, which is cybersecurity and applied cryptography at the University of Northampton. Thank you.